Okay, up to now, we've talked only about single point charges and how we can define the electric field and the electric potential for those. But what happens when you have multiple charges? How does that actually work? So the big idea for this course is actually a concept called superposition. And this is how these kinds of fields add together to give you a net result. The thing that you actually care about is how do all of the charges end up producing a field that other charges then interact with. And so this is a very central concept to electricity and magnetism. It's actually a very central concept to a lot of physics. And this is the first time we're really going to introduce this idea. And we'll talk a little bit about how it's related to force later on. But if we go back and we think about point charges, right? Let's say we had several point charges, at different locations. And we wanted to know what the electric field is due to all of those charges at some location here. Well, what we would do is we would actually determine what the electric field is due to each one of them and just add them up. So, for example, charge 1 maybe produces an electric field that looks like that. Charge 2 maybe produces a field that looks like that, because maybe it's smaller even though it's closer. Charge 4 produces a field maybe that looks like this. Charge 3 produces a field that maybe looks like that. And you'll notice that I did sort of straight line descriptions of the electric field. Turns out all the fields are due to positive charges, right? Because I drew them all as pointing directly away from the points that I've drawn up here, right? The vector sum of all of these individual vectors is the total electric field at that location. So we can just add them all up tip to tail, and we could compute what the net electric field is. So we'll do that mathematically by saying that superposition of the electric field is essentially the sum of all the individual electric fields due to all the point charges. So explicitly, it's like writing down E1 plus E2 plus E3 plus E4 plus anything else you have. So it's basically just vector addition. That's really all we're doing. Now, the thing that we have to be careful about is how we calculate those individual electric fields, because each one of them has a slightly different separation vector, right? So when you're thinking about superposition, you're not just thinking about all of the fields have the exact same description. So let's write it this way. The individual one, the I1, has a form of 1 over 4 pi epsilon 0 Qi, telling you the charge of the individual one, divided by Ri, the separation vector magnitude for the individual one, Ri hat. And all of these quantities can be different for each of these charges. So you have to keep track of each individual one because each of them has a slightly different separation vector, right? The separation vector for each one, while they all share the same observation location, right? The observation location is exactly the same for all of them. It's the source locations that are individualized. They're different for each one. So this all comes into play when you're calculating the electric field for each of those charges before you add them all up. Now, what's really nice about superposition is it not only works for electric field, but it also works for electric potential. So if instead I wanted to know what the total electric potential is at this particular location relative to infinitely far away, I can also add up the electric potential contributions due to each one of the charges that is producing an electric potential. And that's just scalar addition. So V1 plus V2 plus V3 plus V4 plus any more. But remember that each individual one, again, will have 1 over 4 pi epsilon naught, the charge of that individual times the separation vector for that particular charge and the observation location that they all share. What's critical here, and this is sort of a caveat to this, this calculation, adding up the electric field, works all the time. This you have to be a little bit more careful with because all of these potentials have to have the same zero. And that might not get you in trouble in this class, but it might get you in trouble in some other advanced electrical course that you're taking. They all have to share the same zero. of potential to be added up in this way. So for point charges, it's actually pretty easy because they all are 0 at infinity. But for other systems, there might be zeros that are defined that are actually near your observation location. In that case, you have to be very careful about how you add them up. So this video is just to sort of introduce this idea of superposition. We're going to leverage it a lot, particularly the superposition of the electric field. That's going to be a big part of what we do for the next few weeks.